So let's take a look at this new unit, linked lists. Before we get started with linked lists, I just want to go back to something that we've kind of always assumed has been happening. If you do this in Java, you put a line of code like that, the way I've always drawn that since back in grade 10 when you first learned it, was I said inside the computer what's happening is a box is being made called X and a 10 is being stored in there. That's the way I've kind of pictured it. And that's mostly true. But in reality, there's actually a little more than that going on. Okay? What's actually happening in the computer is, yes, there's a piece of memory that will hold the number 10, but the X itself is also a piece of memory. X is the name of the variable, okay? It's the identifier that is connected to its contents, okay? I want to start using a different term to describe this, okay? X is a reference to the contents inside it. To the computer, all of this is memory addresses. It's all just a bunch of mailboxes. This is some memory address, like 00101, and this is the contents, which are stored at some other memory address, like this all the way up to 00109, right? Like whatever. It's storing a bunch of memory addresses. And it takes care of all that. We don't want to know all those details. When we write code like this, we assume something like this is happening. We really don't need to know that it's actually a piece of memory for the reference and a piece of memory for the contents. Okay? Now, that's for a simple data type, like a primitive data type, like an integer. We might end up making something more complex. Let's say we make a class called person, which has a string name and an int age. Very similar to what we did in grade 11 in our example. Okay, so say we make a class called person, and then later on, we instantiate that class. We say person P equals new person. So we do that, okay? Now what we know is going on a more complex level is now there's something called P. P is a reference to a data type called person, and person includes a name and an age. That's what we know is going on there, right? In the sense that that's how I draw it. And if I then said P.name equals Fred, it would put Fred in here. And if I said P.age equals 10, it would put 10 in there. I could also do that through a constructor or some kind of methods. Obviously, as our coding got more complex, we got to kind of this level. But this is still how I would diagram it. Something like this, because that's easier to understand. But in reality, there's even more going on there. Okay? What's actually going on is P is a reference to a bunch of memory addresses, including name, which is a reference to its contents, and age, which is a reference to its contents. And we could keep adding more. So when I go to the reference P, I can then reference things that P references. Okay, again, so now using the word reference, you can kind of see how all this memory is kind of being used and organized by the computer. But we don't need to generally worry about that. We usually think back here, when we write code like this, we're really just sort of visualizing something like that going on. And that's fine. That's the way you should program. But now, we're going to take this to a different level. By using this idea of referencing, we're going to create a structure that's more efficient than one of the structures we already know. If we're going to have a group of things together, if we want to, say, make a game, a Pac-Man game, and we want to collect all the dots in Pac-Man, we know a structure that can store lots of things. It's called an array. Okay? The array can store a collection of items. Okay? It's indexed for us. So we can access things within it. And it's pretty efficient. It's good at storing memory. We could even go up to something like a two-dimensional array if we need it. But there is a flaw with the array. The flaw with the array is its sizing. Okay? So let's say you were going to make a database of every single student in this school. How big would you make your array? Well, you know there's about 1,300 kids in this school. So let's say you made a database for this school, starting at 0, all the way up to 1,300. That gives the ability to store 1,301 students in the school. And all the data that goes into each slot would be stored. The problem with this array is what happens if the school accepts 1,302 students. What we would have to do is we would have to trash this whole collection and rebuild a whole other array that goes up to 1,301. And there's a lot of overhead in doing that, because at each slot in that array, maybe what we're storing is a class called student, and that student makes reference to their name, all their courses, all their grades, etc. A ton of data is stored in each one of these slots, 1,300 of them. And now to add just one kid to the school, I got to trash all of this, copy it all over into here, and then add, pardon me, one more slot for the new kid. That's going to slow me down. But unfortunately, that's the nature of the array. As good as it is, it's locked on its size. The size is locked. As well, let's say students start dropping out of this school. And let's say, although we have an array now of 1,301 students, let's say only 100 students actually register at this school next year. I'm now wasting a whole bunch of memory for nothing. So the nature of the array is, it is a lock size which is efficient, but memory-wise inefficient. What would be better is this structure that starts off as a database with nothing in it. And the second I register a student, it adds a slot for that student. And then the second I register another student, it adds a slot for that student. And then that student. And as well, if a student drops out, it would automatically resize itself so that that student would be removed without having to rebuild the whole thing. In other words, what I'm asking for here is what's called a dynamic structure. One that can change its memory allocation, change its size as it needs to. The problem with arrays is they are what are called a static structure. They're locked in, okay? So a static structure is locked, whereas a dynamic structure is open, okay? It allows you to change it and resize it. But you don't know how to do that. We can only build arrays at this point. So what I'm going to make with you guys is a structure where every single spot in the structure is connected through a link to another spot in the structure. Now, when I use the word link, what I'm really meaning is a reference. It references another structure, like another object. So let's say I'm storing student data. So this is a student. This is a student. Okay? And it would, like the previous one, it would make a reference to another student. This connection is known as the linked, because I'm linking them together, list. Okay? Because it's a list of items. So the linked list structure does this. It connects a bunch of things together, one to the other. When it gets to the end, it still has a link, but it links to nothing. What do we know represents nothing in Java? Null, that's right. It's a link to null, okay? So that's what this will be. Now, the advantage of this structure is several. Every time I want to add a student, I just change this link to connect to a new student. and I just keep adding links to the chain. As well, when I want to remove a student, like let's say this guy wants to go, I just sever this link, or in other words, I point it to null. It's now connected to null, which dumps what's at the end there. Okay? Now there are even more advantages to this structure. Okay? In the sense that if it's like this, a bit longer. One thing usually drawn when drawing linked lists is instead of drawing an arrow here and then putting the word null, we sometimes just put a slash there. That just means that's connected to null. Okay? Now the advantage of this is as well, what if I want to delete something not at the end, but in the middle? In an array, that would be a lot of work. I would have to reshuffle the whole array. I might have to do some sort of sort algorithm or something like that. But in the linked list, it's not that hard. If I want to delete this guy right here, I want him gone, all I have to do is take this connection and redirect it over to here and sever that one. It's like I'm readjusting the connections here. And then this thing is now deleted. It's just that simple. I don't need a whole sort algorithm or anything like that. I'm just essentially removing one piece of it. Similarly, what if I wanted to add it back in? Well, I would just recreate a node, or pardon me, a spot. I'm jumping ahead of myself a little bit. And then I would connect this to here, and I would sever this and connect it to here. And now it's rejoined back in there. All right, I've already said it. One of the terms that's used in linked lists to describe each spot in the linked list, unlike an array where we'd say it's an index, is traditionally the word node. This is a node object. Okay? So that's what we're going to build today. We're going to build this, well, over the next couple days. We're going to build this linked list. We're going to do it in a kind of a more advanced way than just a beginning programmer would. We're going to make classes to do this. So we're going to make a class called the node class. Okay? And the node class will contain constructors and methods and stuff that it can be used for. And because this node class looks like this and it stores data, it also needs this, a reference to, here's where it gets weird, a reference to itself, a reference to a node object. But then we're going to take that and build that into a linked list class. We're going to make a linked list class that has a collection of properties. And the properties will essentially be a bunch of nodes and a bunch of methods, things I can do with the linked list class. What the linked list class will be able to do everything that an array can do and more. It'll also have built in it things like error checking, which is not built into arrays. Right? If you try to access a spot beyond the edge of an array, you always crash. Your program will always crash out on you. But our linked list won't, because we'll build that in. So when you add or you try to get a spot in a linked list, it will automatically error check for you. Okay? So what I'm saying is, if your final project in any way is going to work with some sort of group of structure, like say you're making a game like Pac-Man, or anything where you have a big giant collection of stuff, this type of structure may be a better choice for you. Now, before I go too much further, just like arrays, linked lists are actually already built in to programming languages like Java. Okay? You don't have to make one from scratch. You can actually import these things and use them. And there's nothing wrong with that, but I want to actually dig a little deeper into actually how they work. Okay? So we are actually going to build one ourselves. I'm going to try and build one with you guys that's very robust, and then I'll show you the sort of built-in one that you can use automatically. And there are varieties of them, right? There's one called a linked list. There's one called an array list. There's one called a queue object. There's a few different versions of it, but we're going to start with our own to begin with, because I think that'll give you a better understanding of what's going on with it. Okay, launch NetBeans and set up a new project called linked list, or linked list example, or linked list program, or something like that. Okay, so I'm going to make a project linked list program, and I'm going to let it build a main class for me as well. Okay, so we're going to obviously start in main, like we always do. But we've got to do some work before we can get this program even close to running. Okay, we've got to build some classes around this that it's going to be useful to use. Okay, so before we get started with anything in here, we need to add a new class to our project, a Java class, and you want to call it Node, capital N-O-D-E, Node. Okay, so this is really where we're starting. We're starting with this class called Node. Okay, so our node object, as I drew it before, will be a place where we can store data and a reference to connect to another node object eventually. The question is, what kind of data are we going to store in here? Well, it would depend on the program, right? It could be a collection of integers. It could be a collection of strings. It could be a collection of doubles. But it could be more complex than that. It could be a collection of classes, like class dot that you make for a Pac-Man game. It could be a collection of anything. So I want to actually jump up even another level. I'm going to introduce a brand new kind of thing to you guys. It's a little beyond where you guys are right now, but I think you can handle it. I'm going to make this what's called a generic. In other words, it can be anything. It can be absolutely anything. Now, this gets a little weird. You're going to learn some new code with this, but I think you guys are ready for this. Spark your interest a little bit. In order to do this, to make this node theoretically hold anything, we need to go up to the spot where the node is defined, up here. And beside the word node, we're going to put an angle bracket and a T. Now, it actually doesn't have to be a T. The T is just a placeholder right now. I believe the T is there for a throwback to languages like C++, where they had something called template classes. T, template, makes sense. But the T represents whatever this will be in the future. Because remember, what we're defining right here, right now, is the class and not the object. This is the recipe for what will be a node. Later, we will make a node, we will instantiate the node object, and at that point, we will give it its data type. But for now, we're going to keep it, as Java calls it, generic. Okay. So the node will contain public T data. Now that's weird right there, right? That's strange how that works. Because normally we'd put something like int or string right there. So this T matches this T in the sense that right now it doesn't know what it is. Java has no idea what T is, but it's hoping you will tell it what it will be later. Okay, well, we'll do that. Okay, so we will be able to pull that off. So I just want to kind of show you what this looks like. Okay, so back here in main, if I wanted to actually use the node object, if I wanted to make a node, I would do that. I would say node equals new node, like that. Okay? But it won't be able to pull this off because it doesn't know what node's data type is. Because then if I later say node.data equals 10, it'll have a problem with that because it doesn't know that this is, right now it's not really picking up on the error because it doesn't really get what's going on here at this point. If I try to run this, it'll probably crash. because I haven't quite given it the information it needs at this point. It's trying. First run's always the slowest. No, it was successful. It was able to pull it off. Well, make a liar out of me, will you, NetBeans? All right. Hang on one sec. Let's just make sure I am putting things in the right spot. Okay. Here's the proper way it should have been done. Okay? The proper way it would have been done, you don't have to do this, I'm just showing you, is you have to say node, and then you use the angle brackets here to define the data type. So I could say, okay, node string, called node, oops, equals a new node, and then I once again put the data type right there. So it's a very strange sort of terminology to do this, but this allows me to create a node that holds strings. So then I could go, and again, you guys don't have to type this, node.data equals cat. Okay, so that's holding a string. But in theory, I could do this, node, and I can't use primitive data types. I have to use class types. Node integer, called node2, equals a new node type integer, and then node2.data equals 10. Which is weird. But here I have two nodes, one that holds strings and one that holds integers. But that's the nature of what's called a generic data type. It will morph, it will change into the data type that you need it to be. Okay? This is adding a lot more power to your program. So let's say you made a class called Pac-Man or Ghosts for your Pac-Man game. You could have a node full of ghost types, whatever data type you want, as long as it's not a primitive data type, which allows you to use even simple things like integer here, because integer has a primitive data type and it also has a class type. Anyways, don't want to get too much detail on that. We're not going to worry about that. All you need to know is that this data type can hold anything, theoretically. So now we've completed the first part. We've got a data type that can hold any type of data we want. You tell me what you want. You want to hold strings, we'll hold strings. You want to hold students, you make a student class, I'll do that for you too. I don't care what it is. You will be able to tell me when you define the node what data type it is. But I need to do one other thing. I need to make a connection to another node. I need to make a link there. And we're going to jump another notch. What I've shown you so far in the linked list is called a singly linked list, in the sense that it looks like this. Each node links to the next node down the chain. But from this node right here, I can always move to the next one, but I can't go back. It's like a one-lane highway. It's a one-direction highway. You can only go straight this way, but you can't go back the other way. And it might be the case that at certain points in your programming, you might actually want to create some sort of data structure where you can go both directions. So in theory, we could also make a connection going back the other way. This is known as a doubly linked list, in the sense that it goes forwards and backwards through the list. This is actually even more efficient, because now I can kind of go both directions. And that's what we're going to do. So we'll start with the first one. Underneath that data structure, we're going to make a public node called next. Now, this is where it gets a bit strange, which is why I started with that idea of referencing. Okay? This thing here, next, is a reference to another node object, which is weird. So it seems like it's referencing itself, which it is. It is what's called self-referencing. However, this isn't an object. This is a class. Only when we make objects will this make more sense. So let me show you what I mean by that real quick. You don't have to type this. I just want to show you this for example's sake. We'll go back to here, and let's say I made a node an integer node called n1 equals a new node of type integer. And then let's say I did it again, and I called it n2. Okay, so I have these two integers. I'll say n1.data equals 10, n2.data equals 20. So here's what would be going on inside the computer's memory right now. Okay? It would get to the first line, it would go, okay, they want to make a data structure of type node, so I can do that for them. Okay? I haven't built the constructor yet. We'll get to that in a minute. So let's assume the constructor's been made. Okay? And then it says into n1 you want to put the number 10 because it's going to hold integers. I've just defined that this data type will hold integers. No problem. There we go. Then it goes and makes another one. So this one's called n1. Makes another one called n2. And it puts a 20 in there. That's what would happen. But these two pieces of memory are not yet connected until I might add a line like this. n1.next equals n2. I could connect the two nodes together. It would connect n1 to n2. It would link it. That's the idea, is we are creating a series of connections. Now, if I wanted to, I could even do this. I could say n2.next equals n1. And it would actually take this link and connect it to here, creating what's called a circular list. It's actually called a singular circular list right now. So that's what's happening, is I'm making these connections in the code. Okay? This is how we start to build the linked list class, is through this type of connectivity. But now we're going to go another step. Now we're going to make a public node called previous. Now it's getting even more complicated. Okay? So now I have this going on. Now, well, before I go back to the other one, let's actually build the constructor. Let's make a public node constructor. So when I first make a node, okay, just a generic node, the data will be null. Next will be null. And previous will be null. Do I have to type all three of those lines? Anyone think of a way I didn't have to do all three? Data equals next equals previous equals null is a great idea. It would almost work. The problem is data. You have to actually do that. Can you see why, though? It's a different type. That's right. These two it knows are nodes, so it can easily set those to nulls. That one it doesn't at this point know what it is. So it's going, well, I can set it to null, but I can't set it to next because I don't know, I don't know if it's the same data type. So that's where it has that. But that's just a way you can do that. Okay. So now let's go back to here for a second. On this very first line of code now, here's what happens. It makes something at this point called n1. And n1, according to the class definition, is a data type that will hold a string. Right now I know it's a string. Or sorry, not a string. It's an, my apologies, it's not a string. It's an integer. And I know that because I just said it's going to be an integer right there. But what's inside it is a null. It also has references to something where is the next node and where's the previous node. And according to my constructor, those are also both null right now. So on this line of code, that's what happened. It built that thing right there. A piece of memory that references some nulls. Okay? Then it does the same thing again. Now it builds something called N2. Same thing. Null, null, null. That's what our constructor does. It just makes a bunch of nulls. But then it hits this line right here. And it goes, okay, now N1, your reference to data, which is in here, now will hold the value 10. So this is an integer, but we call it data. That's what it's called. That's its reference name. Then it goes up to N2, and it says N2.data equals 20. Okay? So it did that. But now we get down here to this line, and here it says N1.next, which is right now null, is equal to N2. So now N1 references N2. And then we said N2.next, but you can see here what's going on is we've got a bunch of nulls happening here. What might be more useful is let's link this thing back to this thing. In other words, I shouldn't be writing all these words on here. I'm writing way too much. In reality, I should be doing a lot less of this. Just like I was saying before, what might be useful to you is something like this. We make N1, it references N2, and N2 references back to N1. This one holds a 10, this one holds a 20. That's null, and that's null. That's the way I'm going to start drawing this so it makes more sense. But I want you to be clear about what's actually going on there. This is the type of linked list structure that we're going to hope to build. Is something like that, and then from here we can just keep adding to the chain as we move along here. So that's what's happening. Okay? Okay. Back to the node class. It's looking good, but I think we should overload this constructor. I think it would be useful to us to sometimes make nodes that have the data already built into it. So let's make a public node type that takes T data as a parameter. So how would it look compared to this line? Who can give me the code? What would it look? It would be kind of like this one up here, but slightly different. Well, I'll give you the first. This bottom line would be the same. So this line would be the same. But what would the top line look like? Anyone know? Would it be this? Data equals data? This is a bit of a review. What's wrong with that line? What do I need to add to it? Right. The front, I'd have to say this dot data. Now it's also, which by the way, would mean that I wouldn't need these two lines right here. I could have just put the 10 in here and the 20 in here, and then these two lines, useless. Would have been the same. So that's good. But there might be a time where I actually have a node and I know what it's going to be connected to. In other words, I'd have a constructor that looks like this. Public node T data node next. What would this constructor look like? The first line would be the same. This dot data equals data. But then what would it look like? Well, it would say this dot next equals next, and then finally previous equals null. That's what that constructor would look like. So that could be useful to me right here. I could say 20 connects to N1, which would make this line useless. Because now it's already connecting to a previous or the next node. So you can see kind of how this would work. All right, we're going to make one more constructor now. Theoretically, we could make a constructor that looks like this. Public node T data node next node previous. Okay, so you've probably figured out how this code would go. it would have the same two lines as the previous one, and then this dot previous, oops, equals previous. And again, hopefully you understood that from the classes unit in grade 11 last year, where that reference to this makes sense. Now, let's see if any of you guys actually got a little more on this. So here we have all 4 constructors for this class. Default constructor, one with data and a reference to next, one with data to a reference in next and a previous. But in reality, we can actually shorten up some of these constructors. Do any of you know how? So that they're actually only 1 line of code and not, for example, 2 lines of code. Daniel, can you see how you could do that? How can I shorten this up to just 1 line of code? Well, here's how. In this one here, all I actually have to do is this. What's happening here when I do that is it's saying this with a bracket means call the constructor. So whatever data I pass in here and whatever reference I pass in here are then passed along to here and here. And it looks for a constructor with 3 parameters. Why, here it is. So it now passes that into there. And into this final parameter, it just passes a null. And it would run the line of code. Okay, so if you got that, which some of you may have gotten, how do I shorten this constructor up to 1 line of code? I'll give you the start. What would I put in it? Right, data, null, null. And now, how would I shorten this one? Null, null, null. You got it. Null, null, null. There was nothing wrong with the way we had done it before. I just wanted to introduce that idea to you guys. I said I'd be throwing some bigger stuff at you guys. So just a way to make your code a little more efficient. You can have constructors call other constructors. Okay? If you want. It works. Okay? And believe it or not, there's actually other ways you could do this, right? You could have, up here, just done this. Because this one would then call this one, which would then call this one. But I actually think that's less efficient. Because then you're doing, you're doing a lot of jumping there. So it's harder to track. So I like this one. All the constructors just call this one. This is like the big daddy constructor. It's the one that actually takes care of the work. Okay. Now, that's it for constructors. We got lots of good constructors done. Okay? What I want to do now is write some methods in our node class that should be there. And here's what I mean by that. Going back to main, I'm going to get rid of these nodes. Every single object, every single class in Java, whatever class you make, if it's the node class, if it's the built-in string class, if you make a class called the person class, whatever, every single class you make in Java can have children, like you can use inheritance. But believe it or not, every single class in Java already inherits from a class. It's just done automatically. Every single class in Java automatically inherit from a very generic class called the object class. The object is incredibly simple in Java. It's so simple that rarely is it ever used because it doesn't really have much use to it. But you can use it. I can make an object called object equals a new object. And it doesn't have any constructors. It only has a default constructor. However, it has some methods built into it. Very few, but it does have some. A couple of them at the end here, these wait methods, are used for threading purposes. They're used for the computer sort of running So they're not really stuff that we need to worry about too much. Okay? Similarly, these ones called notify. These are used for what's called threading purposes. They're used for the microprocessor to actually run these in sequence. This one here, hash code, is used for encryption and for storing stuff. It's used for indexing. It's used for memory management. It's not one we usually generally have to worry about. This one called getClass is kind of useless as well. It says, give me the class, and all it returns is the class. So that's not that useful to us either, which leaves us with two that are useful to us. One is the equals method, which is good. Like that's why in strings you have to say dot equals, because it checks to see is this object equal to that object. And the way it does it is it compares all the memory contents, right? Because it could be complex. Does this person equal that person? It might have to look through a whole bunch of stuff. So equals is useful to you. And then the other one, which is this weird one, is most classes provide a method to turn itself into a string. This is good for things like doing simple outputs. Because when you do an output, you may want to just quickly turn your class into a string. So these methods are built into every single object. But we can override those methods and create our own versions of these, which is what we're about to do. Okay? So we're going to go back to our node class, and we are going to override the public string toString method. And we're going to write, this is how you write out a string. This is how it's done. Okay? And it's actually pretty easy. It's just one line. Return, okay, data dot toString. That's it. Because we need to tell it that when you want to spit out a node, you spit out what's inside the data. That's what you spit out. You don't spit out what's inside this or what's inside this. You spit out what's inside that. And we know that the toString method will be built into whatever data type we have. It'll just work. Okay. Now we will write a public, Boolean method called equals. But equals will take a parameter. It will take another node as a parameter, because it will compare, does the node I just passed to it equal me? So all I have to do is I return node.data.equals this.data. Okay, because what I'm checking when I'm checking to see if two nodes are equal, I'm checking to see if its data equals. Now, I could have written this both ways. I could have said this.data equals node.data. Could have done it either way. It doesn't matter. But I'm checking to see, does one node equal another? Okay? Now, we're also going to write two other methods that I think will be useful to this generic data type called node. One of them is a void method called destroy. Sometimes we want to get rid of the node. We want to wipe it out. Okay? To destroy this, I just say data equals null, and next equals previous equals null. That's how I destroy a node. I essentially what's called free up its memory. Now, the thing is, in Java, that's actually not really necessary, because Java has built into it something called automatic garbage collection. And it is exactly what it sounds like. Java constantly uses something called the garbage collector to walk around your code and look for memory that's useless. And if it's memory that's useless, it considers it garbage and it frees it up so your program could use that memory. Because think about it, your computer only has so much memory. Right? If I was to draw a diagram of all the memory within your computer, it is a limited amount. It's not like in math class where we can talk about infinity. The computer has a finite amount of memory. And you might be making some big program that starts using up memory. Starts using it up, using it up, using it up. And then it comes the time where Java goes, well, you know what? This piece of memory right here, this program isn't really using it anymore. So I'm going to now take that piece of memory and free it up so that if they ever need more memory, this piece is now free. That's called automatic garbage collection. Other programming languages, older ones, do not have that. The classic example of the language that does not have this is C++, which is a really good language, but the fact that it does not have that built into it was made C++ famous for what was called memory leaks. It would have code where you might have logic, especially in things like games, where it would be eating up memory over time and it would never give it back. And as a result, you'd run out of memory. Okay? As programmers, when we wrote in C++, we had to deal with that. We had to think about memory management more closely than languages like Java. You don't have to. Also, C# has automatic memory collection. So this method I just wrote called destroy, technically in Java is not necessary. However, if we ever ported our code to another language, then it would be really useful. All right, we're going to write one more method, and I think we'll call it a day. This one can be useful in a variety of different places. It's called the clone method. So we take a node as the return type, and we call it clone. We're entering the world of cloning. What clone does is exactly what you'd think it does. It makes basically a copy of the node that we're currently in. So in other words, it returns a new node. So now it's going to create a new node. But stored inside that new node is this .data, this .next, and this .previous. That's how it clones it. It just does that with it. Creates a new node and returns it. But this is not the same node. This is, by using the keyword new, it is assigning new memory. It'll have the same data and the same two references, but it will be new memory that it's using up this time in this method called clone. Okay, so this is some good programming practices, a little more on the professional end here now, in the sense that we have now today built a very robust class called the node class that has built into it 4 constructors, the ability to turn itself into a string, the ability to compare itself with other nodes, the ability to destroy itself, and the ability to clone itself. The node itself contains, in terms of properties, it stores references to another node, both forwards and backwards, and it can contain data of any data type, generically. This is some serious high-end stuff for today, boys. Tomorrow, we will put all of this into a linked list.